Genevieve speaking. In this chapter, we are looking at continuous probability distributions as opposed to discrete ones. What's the difference between the two? We first looked at that back in chapter 1.23. We pointed out then a discrete quantitative data measure how many. For example, the number of calls received in 5 minutes. Quantitative data that measure how much are continuous. Weight and time are example of continuous variable. Continuous because no separation occurs between the possible data values. In terms of probability distribution, this means x's and corresponding f of x values will have a finite number of values for discrete probability distributions. Continuous probability distributions will have a continuum or never-ending or infinite number of x's values and corresponding f of x values between a given interval. Here we are showing the uniform distribution in the interval a and b. So there is an infinite number of x values between value a and value b, so in that interval. For this normal distribution, x values range from -infinity to +infinity. And for this exponential distribution, we have an infinite number of x values between 0 and +infinity. So for a discrete random variable, for a specific value x0, the probability distribution gives the probability that x is equal to this x0 value, here equal to 1. And here that probability is 0.4. For a continuous variable, it is the area under the probability distribution in an interval between two values x0 and x1 that gives us the probability that the random variable assumes values within that interval. And that's mathematically determined or found by taking the integral of f of x from x0 to x1. Let's try to think why that is the case. So why is that it is the area under the probability distribution in an interval between two values x0 and x1 that gives us the probability that the random variable assumes values within that interval. Let's do that with the normal distribution because that's the one we'll be using most. On the horizontal axis, we have all the possible values x can take, and there are an infinite number of them from -infinity to +infinity. If we look at any interval, for example, between x equal 2 and x equal 3, there's also going to be an infinite number of x values in between those two in that interval defined by 2 on the lower end and 3 on the higher end. So for example, we have 2.5, but in between 2 and 2.5 we also have 2.25, and so on and so on. So we have an infinite number of x values. On the vertical axis, we read the values of f of x. Higher f values indicate that corresponding x values are prevalent or occur often in our distribution. Lower f values indicate that the corresponding x values are not observed much in the distribution of all possible values. For our normal distribution here, x values are far away from the mean, much lower than the mean, so on the left side, or much higher than the mean on the right side, are rare or extreme. Once I've accounted for how much of the x values within each tiny interval of values I've got, then I've accounted for all of them. And by doing so, I've traced the whole surface area under my curve. So the surface area under the curve in an interval of x values gives us the probability that the random variable assumes values within that interval. What's illustrated here is the interval that contains all the possible x values. So the probability that the random variable assumes values, all the possible values or values within that interval, is 1. Because our normal distribution is symmetric around its mean, half of our x values are found above its mean, and so the probability that x values are greater than or equal to its mean is 0.5. And half of our x values are found below the mean, or the probability that x values are equal to or less than the mean is 0.5. Because the normal distribution is symmetric around its mean, the proportion of x values between the mean and mean plus 1 standard deviation is going to be the same as the proportion of x values found between the mean and the mean minus 1 standard deviation. And because any normal distribution has this unique and precise bell-shaped curve, for any normal distribution with mean mu1 and standard deviation sigma 1, the proportion of x values within its mean and 1 standard deviation is going to be equal to the same as the proportion of x values for any other normal distribution between its mean and 1 standard deviation. This is why we can use proportions for the standard normal distribution to determine proportions for any other normal distribution in our problems. Here we've illustrated the case where x is between its mean and 1 standard deviation above its mean, but this is true whichever interval of x values we're looking at. This is the algebraic expression for the normal probability distribution. So it means if we plug in x values and we're going to get f values, corresponding f values, and if you plot that, we're going to get this unique bell-shaped curve, and we want to show that. We're going to show that in Excel. So in Excel, this is the function normDist. Its syntax is similar to the one we've looked at before for the binomDist function. Its arguments are straightforward: x value, mean and standard deviation. The last one being the cumulative argument, set to true to get the cumulative probability, and set to false to get the value of the function f at a specific value x. Each normal distribution is uniquely defined by its mean, mu, and standard deviation sigma. We want to work here with the standard normal distribution, which has mean equals 0 and standard deviation equal to 1, so that's the value as we specify. Next we call up the normDist function, and we are going to compute those f values for x values ranging from -4 to +4. So we need the x value. First we are going to get that from cell F5. The mean is found in cell B1. We put a dollar value on that, around that cell for reference, because next we're going to copy that formula down and we don't want that cell reference to change. Standard deviation, same thing. And here we want to plot that normal distribution curve, so we don't want the cumulative values, we want the f value specifically. So next we want to plot the x values and corresponding f values. So we select the x and f columns with our values, and then we go to insert on the scatter with smooth line, I think. Yes, here we go. We get our bell-shaped curve symmetric around its mean. So it is this formula that gave us this shaped curve. We relabeled our axes z and f of z since we are looking at the standard normal distribution with mean equal 0 and standard deviation equal 1. Here we've reproduced the left-hand page and also over here the right-hand page of the standard normal distribution table found inside the front cover of our text. So similarly to what we had done before, reproducing tables 5.14 and 5.15. So back to the left hand page, I have an image of it here in my PowerPoint for the purpose of this presentation. So each value in the table is an f value computed for each z value. So the z value as opposed to x value, because we are looking at the standard normal distribution with mean equals 0 and standard deviation equal 1, which we specified as our second and third argument for our function. Here we're looking at the z value minus 2.95. That z value up to its first decimal place is specified in what we can consider the rows labels, and its second decimal is specified in the columns labels. So here our first argument tells Excel to get the value from cell A4 and subtract from that the value from cell G1. So minus 2.9 minus 0.05 equal the minus 2.95 we're working with. I have dollar signs around the cell reference for G1 because I had written this cell reference and then copied down below. And when I did that, I didn't want that cell reference to change. Last argument, we set it to true, because that's what this table on the front cover of our text gives us, cumulative probabilities. So here the probability that z has a value equal to or less than minus 2.95 is 0.0016. If we want to determine the probability that z takes a value equal to or less than minus 0.81, we look up the table value located at the intersection of the row label minus 0.8 and the column label 0.01. So we get 0.2090, which means that the probability that z has a value less than or equal to minus 0.81 is 0.2090. Now how about the probability that z is greater than or equal to minus 0.81? Because the whole area under the curve in blue represents the total probability of getting all possible values, or 1, we can take 1 and subtract from it the probability that z is less than minus 0.81 to get the probability we were looking for, that z is greater than or equal to minus 0.81. Now, if instead of a standard normal z variable, we have an x variable, so normally distributed, and here with mean 2 and standard deviation 0.5. We'd like to know what's the probability that x is less than or equal to 1.595. Because the cumulative probability for value x is the same as the cumulative probability for value z, when they are both located at the same number of standard deviations away from their mean, we can just figure out how many standard deviations away from its mean x is, so getting its z value, and then look up the cumulative probability for z, which is equal to the one for x. The z value corresponding to our x value is equal to minus 0.81. So the probability that x is less than 1.595 is equal to the probability that z is less than minus 0.81. And we had just figured that out, and it was 0.2090. But of course, we don't have to use the front cover tables. Instead, we can use Excel and directly compute cumulative probability for whatever normal distribution we're working with, without going through the intermediary z value. So let's do that. Calling up our normal this function, getting the x value from cell F5. The mean for our problem is 2, and located in cell B1. Standard deviation in cell B2 equal to 2.5, and then we are looking at the cumulative distribution, so we want to set our last argument to true. This way we clearly get our 0.2090 probability value. We've used the norm_dis function in Excel. It's flexible enough that it can be used for any normal distribution, standard or not. Now we want to look at the norm inverse, or env function. The norm_dis function is used to determine cumulative probability for any normal distribution. So x, mu, and sigma, so mean and standard deviation, were known, and the cumulative probability was the unknown. The norm.env function returns the inverse of the normal cumulative distribution for a specified mean and standard deviation. So it's used when the cumulative probability, the mean mu, and the standard deviation sigma are known, and the x or z value is the one that is unknown. Returning to our previous problem, now we're looking at for the x value such that the probability of all x values are less than or equal to this unknown one, so that this probability is 0.209. So we're going to use a norm inverse function, get our probability value from cell F5, mean and standard deviation from above. Here we go. And we do get 1.595 as we expected to. And this concludes our presentation on the continuous probability distributions, mainly the normal distribution.